We're going to be talking about inscribed angles in a circle and how to find the measure of an inscribed angle using the measure of the included arc. This is going to be an algebraic explanation to derive the general rule. I've also made a video with a numerical example, so if you find that easier to follow or if you want to watch that one first, I will link it in the description. We're going to start off here with a circle with an inscribed angle, and I've labeled the included arc as x degrees. So our goal now is to find the measure of that inscribed angle in terms of x. First thing we're going to do is we're going to draw in a central angle so that we can label that central angle as x degrees because the central angle and the included arc have the same measure. From there, we're going to connect the endpoints of those angles with another segment. And the reason we do that is that that makes a lovely little isosceles triangle here. We know that this triangle is isosceles because two of its sides are radii of the circle, which means that they're congruent to each other. And then because this triangle is isosceles, we know that the base angles are congruent. Little bit of algebra is going to tell us that each base angle here is 1/2 of 180 minus x, because all three angles together have to add to 180. If you do 180 minus x and then divide by 2, that gets you the two base angles. From there, we're going to draw another radius connecting that center point to the vertex of our original inscribed angle. Reason we do that is that it's going to get us two more isosceles triangles. One of those isosceles triangles is down here. We don't have a lot of information about the measures of the angles in this isosceles triangle, but we do know, once again, that the base angles are congruent to each other, so we can label them both y. And then our third isosceles triangle up here, we're going to label both of the base angles z. So right now, our original inscribed angle has a measure of y plus z, and our goal is to find y plus z in terms of x. In order to do that, we're going to look at this great big triangle inscribed in the circle, whose angles are made up of the base angles of our three isosceles triangles. And since we know that the angles in a triangle have to add to 180, we're going to be able to get an equation in terms of x, y, and z, and then get x alone in terms of y and z. We'll make this smaller so we've got some room to work. And the equation we're going to write is 2y plus 2z plus 2 times 1/2 of 180 minus x equals 180. So that came from adding up the base angles in our three isosceles triangles because those make up the vertices of the big triangle that we're dealing with right now. 2 times 1/2 cancels out, so this can become 2y plus 2z plus 180 minus x equals 180. Subtracting 180 from both sides gives us 2y plus 2z minus x equals 0. Our goal is to get x on its own, so we're going to get x over here on the right-hand side by adding both sides. And then we want to get y plus z because that's the measure of our inscribed angle. We're going to factor out a 2 and say 2 times y plus z is equal to x. Dividing both sides by 2 tells us that y plus z equals 1/2 x. So y plus z is our original inscribed angle, and we're now saying that it is half of x, or half the measure of the included arc. So that looks like this. Anytime you have an inscribed angle in a triangle, you can say that the measure of that angle is half of the measure of the included arc.